Go through the integral test first, and then I don't know if I'll have time for a comparison test. So let's see if we can first read what the heck this says. The integral test says that you're trying to look at a sum, n equals 1 to infinity, a sub n. So you're trying to look at this series, right? This is integral is what I'm doing right now, integral test. You're looking at this series, you're having trouble figuring out what it's doing, all right? It doesn't fall into any of the categories that we've looked at so far. So you're like, all right, what do I do with this? Well, you transform the sequence into a function. And I'm going to say a function of x because that's the way I do the entire homework set on video. So I'm transforming my sequence, which is a bunch of dots, over to a function, which is a function of all real numbers. We've done this before, haven't we? OK. This test says we have to have some conditions. If, and this is, I'm looking at the far right side of the table, on the comments, if f is continuous on 1 infinity and f is positive on 1 infinity and f is decreasing on 1 infinity. I'm going to add something to this. We actually don't need that strong of a condition. Do y'all remember what it means for a function to be decreasing? It's going down from left to right? OK. We actually don't need it to be decreasing on the entire interval. It really can just be, instead of this, what I will say eventually. So it can kind of, the function that we come up with from the sequence can go up and down a little bit, but eventually it needs to go down and keep going down, right? And stay going down the rest of the way. OK? And the last thing, I don't want that in red. And f is integrable. What does that mean? You can integrate it. Integrable. Weird word, huh? So summary, I haven't said what the test says yet. I've just shown the conditions for the test. You have to be looking at a sequence. You have to know. You have to basically be stuck on it, and then you have to say, wait a minute, hold on. If I turn that sequence into a function, like from just a function of normal variable x, then as long as that function is continuous, I can draw it without picking up my pencil. As long as it's positive, always above the x-axis. As long as it's eventually decreasing, and as long as I can integrate that function, then here's the result of this. What is the result? Then, I'll put it up here. Then, if the integral of the function on the interval 1 to infinity converges, so does your series. On the other hand, what do we mean by the integral converging? It's going to give a finite number. If my integral, when I do my integral, if it turns out to be a finite number, what that tells me is that my series had to do the same thing. And then the other result is, if the integral diverges, guess what? So does my series. This is an awesome test. It just kind of sucks to apply it, OK? It's not fun to apply this test, but it's powerful. and every Cal 2 student should know how to apply the integral test. So let me see if I can convince you quickly as to why this works. All right? Remember that when we have a sequence, it's just a bunch of dots, right? And when we add them up, we get the series. Right? That's what a series is, it's just adding up a bunch of numbers. So imagine I have a sequence that is eventually decreasing. Right? Like this. And notice I'm staying above the x-axis. Why am I staying above the x-axis? Because I have to stay positive also, right? So I have a function, I've got a sequence that's decreasing. If I, instead of looking at the sequence of dots, use a function instead, right? That's f of x. I have a continuous, nice, smooth curve. It is positive above the x-axis and it is decreasing. Then what does this integral represent? Geometrically, what does that integral represent? The area underneath that red curve, doesn't it? It means starting at 1, find that area, right? If that area is finite, then the sequence has to be finite. Because, or the series does, because isn't the series just adding the heights of each of these lines? Isn't that? Right? I take whatever the first number is, I stack this one on top, that one on top. So you're just adding up all these lines, these lengths. Those lengths have to be less than the area, doesn't it? So if the integral converges, so does the series, right? On the other hand, if this area is infinite, the series has to be infinite. That's not as easy to show. And I can't prove it in here. Okay? It's not part of this class to prove why this second one is true. This one might be hard for you to convince yourself of. If this area is infinite, does that mean that the black lines have to be infinite? Well, it turns out that we've proven it does. Okay? So we won't argue about that. This one's easy to show, I think, geometrically. This one's a little harder. All right? You want to see this in action? Of course you do. Here we go. Let's take the series converge or diverge. Sum n equals 1 to infinity. Yeah. Natural log n over n. What should we start with? What's that? Nth term? You want to just try real quick? Nth term test? Okay, nth term. Nth term, limit, n goes to infinity. What am I hoping for here? It's not 0, right? That's what I'm hoping for. So right now I'm infinity over infinity. One application of L'Hopital's rule. 1 over n over derivative natural log 1 over n over 1. Where does that go? 0. Fail. Cross it out, whatever. Right? So that didn't work. Okay, is it geometric? N's not in the exponent. Is it harmonic? It's not a constant over linear. Is it a telescopic? Is there a way you could split it up so that you could get subtraction in there? No, because that natural log, you can't split it into two logs because you would have to have division inside of the log. This is division, log separated from something else, right? What else do we have? Is that a p series? Well, it's n to the first power, but the top would have to be like a number, like 1. So it's not p series. So it's nothing we've seen, right? So what you would want to look for before you start thinking integral test is you would like to look at the inside, look at the sequence in here, write it as a function of x. And before you even start this, ask yourself if you would ever want to integrate that. Because if you don't want to integrate it, I wouldn't try the integral test. Could you integrate that? Yes? That's a basic u sub, right? If u is what? Something has derivative. So do you see the something? Natural log x, what's its derivative? 1 over x, it's there, right? So you can integrate that. Okay, so maybe the integral test. So I'm thinking integral test right now. So I'm going to write it down. Integral test. I'm letting everyone know what I'm about to do. This part of what I'm doing is really important. All right. When I do the homework videos, if you watch those, I try, at least for the first 20 or so problems, I'm very meticulous about the way I write things because that's what I expect for you to do on a test. You need to show me each test because all I'm asking is convergence or divergence, right? If you just have a bunch of chicken scratch everywhere and it's just like your random thoughts all over the page and at the end you get divergence, but I can't tell what in the hell you did, but you're right, I can't give you full credit. I have to be able to follow your logic. And so I need to see, okay, you tried nth term test, it didn't work, you stated that, you moved on to integral test. I see you showing all the things you need to do integral test, doing your integral properly, you know, and drawing your conclusion. If you get an incorrect conclusion but you show all your work, you get partial credit for that, all right? Because at least you're going through a procedure, a process. All right, so what do we need for the integral test? We have to have conditions met before we can do it. Okay, you have to show all of this. If right now you just set up an integral, if you do this and you get your answer, you're going to get like, if this were 10 points, you would get 2 points. You have to show me you can use the integral test before you use it. You ready? So what's the first thing I need to show? F continuous on 1 infinity. This is the question. Is it? Why? Natural log is continuous. X is continuous on 1 infinity, right? Because at 0, they're both in trouble, right? But I'm not looking at 0. So is this? Yes. Ratio of 2 continuous functions. This part of chapter 8 is really where I start to notice the differences in students and just how well people can organize their thoughts and put them on paper. Because as an engineer, or whatever it is you're going on to do, whether it be biology or whatever, getting the information from here to on a piece of paper where you can hand it to a colleague and they can go, okay, got it, I understand what you're talking about. That is a skill. That is something that you acquire. All right, so what you want to be thinking about when you write this is, are you communicating what you're doing to whoever is reading this? I think I have, right? Yes? All right. What's next? F must be positive on the interval. Question, is that true? It is? Okay, so let me show you why it's positive. I need to show you that natural log of x over x is greater than 0, right? That's what I need to show you? Right? Is that true? Is natural log of x always positive? Not always, right? What does natural log of x look like? Looks like this, doesn't it? Isn't it negative sometimes? But where does it switch?
1.
At 1, right? And where am I looking? 1 to infinity, right? So at 1, isn't this 0? Yes? But after 1, what is it? The top's positive, and of course the bottom is going to be positive because x is positive. So there's only one place where it's not positive, right? So this condition of being positive on the interval, do you think I violated it by being not positive at one point? It turns out it's okay as long as after that it's positive. So we are still okay with this, all right? So this is checked because natural log of x is greater than or equal to 0 on 1 infinity. That's that. And of course, x is greater than 0 on 1 infinity. So if I take a positive number and divide it by a positive number, I get a positive number. F decreasing on 1 infinity. But I said you don't have to show that much, do I? Do you? I said what? Eventually, right? Who wants to tell me how they would figure out if a function is decreasing? Anyone have any idea of how you could show me whether or not a function decreases? You could just look at, like, plug in values. That's a way of convincing yourself it's decreasing sometimes, but how do I show you it's decreasing on the entire interval? Think Cal 1. What was Cal 1 about? I'm doing this in my Cal 1 class right now. I did it yesterday. I did it. What do we have to look at to figure out if a function is increasing versus decreasing? The slope, right? The derivative. If the derivative is positive, the function is going up. If the derivative is negative, the function is going down, right? So all I need to do to show this is prove to you that the derivative is negative eventually. Do you agree? Is that enough for you? So I just need to show you right here that the derivative of f is negative. If I can do that, I hope you'll be convinced. Well, you better be, because that's what Cal 1 said happens. Okay, so that means we have to take the derivative of the function. What's the derivative of the function? Well, guess what you're going to have to do for that? Quotient rule. The quotient rule. Do you see why I said if you just do the integral right at the beginning of this problem, you're just going to get 2 out of 10 points? There's so much framework that has to be established before you can use the actual test that if you miss all this, you're missing like really the whole heart of the test itself. All right, so I'm going to take the derivative of the function itself, the derivative of that quotient rule, derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Agreed? And this is equal to, simplifying 1 over x times x is 1 minus natural log x over x squared. Now I need to convince you that this is negative. Eventually. What can you tell me about the denominator? If I'm plugging in numbers from here, right? These numbers down here are always positive. Actually, the fact that I square it doesn't matter, right? But do you agree that the denominator of this is always positive? Okay, what can you tell me about the numerator? It's negative what?
Negative.
Well, 1 minus this, right? Is this going to be positive or negative? Is it always, though? Because what's natural log of 1? 0, so you get a positive, right? What's natural log of 2? Well, again, you go back and you look at the natural log function like this. At 2, it's somewhere, right? But eventually, right, this number will be bigger than 1. When I say that, I'm saying this number right here will be bigger than 1 eventually. And so we're going to eventually get negative. So the further you go out, the more you, well, I shouldn't say it that way. I should say that with this function, initially your derivative is positive, so it does go up, but eventually your derivative will switch to negative. It'll start coming down from this right here. Do you all see that or not? Yes? So I'm going to say that this is negative when 1 minus natural log of x, what, is negative? Which means when the natural log of x, I just moved this over, as soon as the natural log of x gets bigger than 1, this is true. So eventually. All conditions are met. Continuous function. It's positive. It's decreasing eventually. It's integrable, because you told me in the very beginning you could integrate that. So since I've got all the conditions met, I can apply the test. Any questions? Here comes the test. The test is, I'm going to look at the integral from 1 to infinity of natural log x. Natural log x over x dx. Whatever this does, my series does. See, what will happen is someone will get a problem on a test, and they'll look at it and they'll be like, oh, I can integrate that. And they use the integral test, and they don't go through all those checks, and it turns out that one of those checks isn't true. And they get a conclusion that's completely wrong because the conditions weren't met. All right. So? First, I'll make it an indefinite integral. U sub. And that turns this integral into what? What is it? U du? U du? Antiderivative of u du? 1/2 u squared. But what's u here? Natural log of x. So natural log of x squared. That make sense? Yeah, I'm only saying that because it's been a while since we've done this, so hopefully the gears will start turning again for that. All right, now we go back here and we say, all right, we got to just do this now, right? But this was called an improper integral because one of the limits was infinity. So whenever we saw that, we had to change the integral into a limit. So I'm coming back to this now, and I'm going to say this is equal to the limit as t goes to infinity, integral 1 to t of natural log x over x dx. That look familiar? We replace the infinity with t, and then do the limit. And we just said that the antiderivative was 1/2. Oh, wait, I forgot my limit. Limit t goes to infinity, 1/2. Come on, Robert. Natural log x squared 1 and t, like that. Oh, man, are you kidding me? All right, limit t goes to infinity. All right, let's plug in. T goes in here, right, first. So you get 1/2 natural log t squared. That's what you get if you plug in t. And then minus, now plug in 1. Oh, natural log of 1 is 0, so this is just 0. And now let t go to infinity. Natural log of infinity blows up, right? This diverges. This goes to infinity, which means it diverges, right? The integral diverges. Therefore, series n equals 1 to infinity, natural log n over n diverges by the integral test. There, little happy face at the end. That only, that took about 20 or so minutes, 25 minutes. Well, right, breathe in, breathe out. I told you that chapter 8 is relentless, right? It's not gonna let up. It's just gonna keep coming. So that's why I said breathe in, breathe out. How about the comparison test? Well, here's how the comparison test works. And I think I can summarize this one pretty clear. Let's see. Let's say that I have a series right here that I don't know what it does, right? And then I've got this other series over here in red. And I do know what it does. All right? Now think about the word for this test, comparison. You're going to compare, right? So what if I told you that this one converged? All right? And then I show you that A sub n is always less than B sub n. What would you say? That this one has to converge. So it's like, look, if I have all these guys in here, and I add them up, and it comes to be a number, and then I show you that all of these guys are always smaller than all of these guys, then doesn't this have to add up to be a number also? What? So glad you asked. So there is one condition on this test. We have to be looking at both of these being positive. So the assumption here is that A sub n is positive and B sub n is positive. All right, so imagine I'm adding up a bunch of positive numbers, right? And I add them up and I get a number. Then if those positive numbers are smaller than these positive numbers, then that must add up to be a number. No? Is this not? Are you being just agreeable with me, or?
No, it makes sense.
It does make sense? Show of hands? Makes sense? Let's look at two sequences. I'll draw it. Let's say I have B sub n is going to be in black. Here's the sequence, okay? Let's say I take all those little lengths, I add them up, and it comes out to be a number. All right? That's B sub n. And then I tell you I have A sub n is always below that. Then all of those should also add up to be a number, shouldn't they? If adding up the heights of the black ones comes out to be finite, then adding up the red ones should be finite also. Yeah? All right, let me reverse this on you. What if I tell you this diverges? So we don't know what this is. I know what this is and it diverges. Then how can I use that? What if I show you the other way? That all of these guys are always bigger than all of these guys. Then what will happen? This one's going to have to diverge also. So there's two ways that we do comparisons. We look at a series and we say, I don't know what it is, but it looks kind of like something I do know. And I determine whether or not I can say that converges or diverges. Then, once I determine if it converges or diverges, I try and figure out what I'm going to need to show you. Now, this is all stated in the test, but it's hard to read, so I think it's best if I show you an example first, and I have just enough time to do one. Are you ready? Okay. I know you're ready, so here we go. Converge or diverge? Sum. N equals 1 to infinity, n over n cubed hold on. Plus 1. Okay, let's see what we can do in the next 9 minutes with this. All right, so nth term test. So n goes to infinity, infinity over infinity. L'Hopital once, 1 over infinity, goes to 0, doesn't do anything for you. Okay? Nth term test fails. Is it geometric? No. Harmonic? No. No. Collapsing? Maybe. You might be able to factor the bottom, but I wouldn't even do that. I wouldn't mess with that at all. Okay. Integral test. Would you want to integrate that? Could you integrate that?
Yeah, because you could and then you just use U sub.
What's the U sub though?
N squared.
Yeah, if you had an n squared up top, that'd be nice to integrate, wouldn't it? But it's not n squared up top. So maybe not. How about a comparison? Can you think of a series that looks kind of like this one that you do know something about? So let me help you, because this is our first example. Think about if n is really big. If n is really big, do you really think this one matters too much? No, it doesn't really matter, does it? So like if you look at this series, that's pretty darn close to this series, isn't it? Except that little one. So I want to compare these two together. Now, do you know what series this is? What type of series? It's really 1 over what? N squared, which is what type of series? That's a P series, you see? That's a P series. With P being what? P being what? 2, which is greater than 1. So what does this P series do? Converges, doesn't it? Are you all with me? Starting with the series that I don't really know what to do with, I realize it kind of looks like this one, which is something I do know, right? And I know it converges, right? Big C over here. Big C over here converges, right? So that means if I start stacking all these numbers on top of each other, it comes up to be finite, doesn't it? This stacks up to be finite. I'd like for this one to also be finite, which means that all of these guys would need to be what? Bigger or smaller than all of these guys? All of these have to be what? Smaller than all of these in order for them to both be finite. If these are bigger than these, then I can't tell you what happens. You all see the difference? Okay. So what I would need to show you right now, right? What I want to show you, I want to show that A sub n is less than or equal to B sub n. That's what I want to show. Now what do I mean by A sub n? This is A sub n, and this is B sub n. But there is one thing we have to check for before we can do it. We have to convince ourselves that both of these, the A sub n and the B sub n, are both positive. If they're not positive, if there's a chance that these are negative numbers, then we run into a whole different issue, and that's what the next section is about, which is what happens when these are negative in here. Okay, so are these both positive? Yes. N is positive, that's positive. This, of course, is positive. So I'm going to check. I'm going to go for this comparison test, all right? If I can show you this is true, I'm done. All right? If I can show you this is true, I'm done. Now, how many of you did that homework where I told you to look at those ones where it was the bounded monotonic? I said, watch the video. I said, you won't realize why you need to do this later on, and we'll have to do it. This is why. It's to set up this inequality and be able to work through it. So what is a sub n? N over n cubed plus 1. I need to show that that's less than or equal to 1 over n squared. If I can show that, I'm done. So what did I do in my videos when I had that? Please, not all at one time. I don't like it when you talk over each other like that. It's very rude. What do you do? Yes, I guess you could say that, but you don't need to add.
Okay, I think you just put it back into
N squared here, n squared here. That'll clear out the n squared here. And then you also multiply n cubed plus 1 here, n cubed plus 1. Now, I think in my videos I called this cross multiplying, but what happens when you do that? That's gone. That's gone. So what are you left with on the left side? N cubed less than or equal to, what's the right side? N cubed plus 1. Now what? Nope, just, nope. You're not letting n go to infinity. You stop when you're convinced, and you convince me that that's always true. That is always true? Okay, I was just going to ask you to subtract n cubed on both sides. Subtract n cubed on both sides? And what would you be left with? Is that true? Absolutely, that's true. So what we said is we started with this, and at the end of our work, we came up with something that we all agree on, yes? That means this inequality is always true. Which means that when you stack when we're stacking up the b sub n's and adding them together, it's finite. And each of the a sub n's is even smaller than the b sub n's, so when we stack those up, it should be finite also. Yes?
So whenever we're going to be using this comparison, we might have to use it in conjunction with another one of the tests. Like, it's how we use a p-series to kind of set it up. Or would it be like one of those simple ones?
It would mostly be simple, but it could be like you're comparing it to a geometric series.
Yeah.
Yes, but I wouldn't ever do something where like you're comparing it to a telescopic that you have to go and figure out what the telescopic's doing. It would usually just be one step back, if that makes sense. Or harmonic, okay? So am I done? No, I'm not done, because now I'm going to conclude. I'm going to say, therefore, the series n equals 1 to infinity of n over n cubed plus 1 converges, I don't know what to, by the comparison test. Done. Again, all the work that I showed in that problem is what you have to show. And you're just going to have to get your hands dirty with the homework. I'll give you what the homework assignment is for this section. You cannot do all the homework in this section yet. But if you watch my videos for the homework, you could probably follow along for quite a ways. Page 453, numbers 6 through 30. That's what I did. That's what I did, yep, 6 through 30. All. So I think what would be probably a good, fair test on Tuesday. That's, man, you know what? I didn't have this on my Cal 2 test. I mean, you know what I'm saying? Like, I didn't have this on my Cal 2 test, so do you think you actually need this? I mean, right now at this point, this is what I'm saying, you would only have on this test up through integral test. I would not put comparison test on there for you. Okay? So if all you had to worry about was n-term geometric p-series and integral and telescopic, I mean, think, you tear it in half now. I've told you before, I'm not big on, memorizing. I'm not a memorization person. But at the same time, like, You have to understand these tests. You have to understand why you can use them, how you can use them. Let's revisit that question next class. So my plan, though, is this. Next class, we will continue into 8.3. We'll get into comparison tests. We'll do more comparison tests. Then comes what's called the limit comparison test. Then after that, we get into alternating series test and ratio test and root test. And that'll get us through all the tests. There's no way we finish that next class, though. Here you go. So your test will cover, I know you want to go. I guess you can. I can talk about test next class. Just get caught up with this homework assignment, at least the first, where is it? 6, 7, and 8. 6, 7, and 8 out of this homework assignment are integral test problems. So it even tells you, use the integral test to figure out. So those, every homework assignment I've given you up to this point, and this 6, 7, and 8, that's what would be on the test. And we can talk about the test in more detail next class. Have a good day.